Let's look at a standard corporate boardroom. A management team presents projected returns for a new strategy. The math is spotless. The expected value calculations point straight up. The unit economics are sound. Yet, the presentation is missing a vital page. There is no analysis of path dependency. No one is asking what happens to the capital pool if the first two bets stumble, leaving the third initiative severely underfunded. Because this analysis is missing, organizations with highly profitable products and intelligent leadership quietly drift towards insolvency, completely baffled as to why their meticulously crafted plans failed. The error originates in the foundational math. Expected value answers a specific question. What happens on average across thousands of parallel universes? Your business does not exist in parallel universes. It operates sequentially, moving step by step through time, using the finite pool of capital it has left over from the previous quarter. Applying a parallel universe metric to a time-bound business is called an ergodicity violation. Using expected value to allocate sequential capital is mathematical malpractice. To see exactly how this breaks a company, we can run a thought experiment designed by physicist Ole Peters. Start with $100 and flip a fair coin. Heads, you get $150. Tails, you drop to $60. The expected value is straightforward. A 50% chance of $150 plus a 50% of $60 equals $105. That yields a 5% expected return on your initial stake. Statistically, any rational actor should accept this bet. If the math favors one flip, you let it ride. You keep flipping the coin, compounding positive expected returns over and over. Expected value tells you your wealth will climb indefinitely. The reality of sequential compounding guarantees you will go broke. Let's map out why that happens by testing the difference between a parallel ensemble and a sequential timeline. On top, 1,000 people play simultaneously. Their collective wealth rises steadily, proving expected value correct. On the bottom, a single person plays the same game 1,000 times sequentially. Variance creates wild swings, but inevitably, the median outcome collapses. The player is wiped out. This ruin is not caused by bad luck. It is a mathematical certainty built directly into the sequential process. This divergence is called non-ergodicity. A positive outcome for the group is actively masking a terminal outcome for the individual moving through time. The failure occurs because capital evolves over time as a product, not a sum. If you win 50% to reach 150, then lose 40% on the next flip, you don't break even. You drop to $90. Multiplicative processes compound asymmetrically. To analyze a multiplicative process, use the geometric mean. The equation takes the win condition, multiplies by the loss condition, and finds the square root. It resolves to 0.949, meaning the true compound return is actually negative 5% per round. Expected value generates a highlight reel. The geometric mean shows you the actual game film. This flowchart translates the coin flip into a corporate strategy document, detailing 5 sequential initiatives, drawing from a central resource base. Each project is modeled independently, boasting a mathematically sound, independently verified positive expected value. The company launches the first 2 initiatives. They underperform slightly, shrinking the central resource pool. The third initiative now draws from a depleted base. Launching underfunded, the reduced capital limits its probability of success, and it fails completely. Organizational patience snaps. The board demands a recovery win. The team enters make-it-back mode, designing Initiative 4 with massive upside to plug the hole, introducing extreme variance right when they need stability the most. Under the strict rules of expected value, every decision made in this sequence was correct at the time it was made. But by ignoring the constraints of the sequence, the team steered a sound strategy into a mathematical death spiral of loss chasing. The solution to this structural trap was derived in 1956 at Bell Labs. John Kelly Jr. was analyzing a communications problem: how to maximize the amount of information pushed through a noisy wire without destroying the system itself. He realized that extracting signals from a noisy channel and placing bets at a casino are mathematically identical problems. He derived this formula, now called the Kelly criterion. It is designed exclusively to maximize expected logarithmic wealth, the only type of wealth that survives compounding. Feeding the probabilities of Ole Peter's ruinous coin flip into the formula calculates the exact fraction of your bankroll to risk. The optimal point is 25%. Risking a quarter of your capital per round makes the ruinous game highly profitable. The probabilities didn't change. The expected value is identical. The only variable that changed was the size of the position. Strategic failure is rarely about bad ideas. It is almost always about over-leverage relative to the volatility of the sequence. This mathematical framework exposes a persistent source of malpractice in the modern startup ecosystem. This diagram maps out the venture capitalist's view on the left. Operating 50 concurrent portfolio companies, they genuinely live in an ensemble world where localized failures average out against massive winners. On the right is the founder. They operate a single sequence of bets in strict time. 2 early failures do not average out. They compound, exhausting the capital base and terminating the game. When a board member says, "Scale faster, worry about margins later," they are giving mathematically defensible advice for their own parallel portfolio and structurally fatal advice for the sequential business receiving it. The power differential in the boardroom masks the reality that the investor and the founder are playing categorically different statistical games. If you allocate capital or design strategy, you have to operate inside the correct framework. Stop presenting expected value as proof of viability. Run Monte Carlo simulations to test the specific path your capital takes to ensure the early drawdowns are survivable. Treat volatility as a strict tax on growth. Apply the Kelly criterion to cap your exposure relative to your capital constraints. Convert sequential problems into parallel ones. True diversification allows averaging to work before your runway is exhausted. A competent team does not maximize the projected return of an isolated decision. They size bets to absorb early losses and maintain the capacity to keep playing. Strategy models that ignore ergodicity are broken by design. Understand the sequence, protect the base, and force the compounding math to work for you.